For you, the best thing to get when we talk about cancer chemotherapy is a kind of overall sense of how we treat patients with cancer at the moment, and also what's coming up in the future. Because this is obviously a very specialist area as far as the pharmacology goes, I don't see that there's a benefit for you of learning lots and lots of anti-cancer agents, because there are hundreds and hundreds of them. So what I want to do in this part is give you an overview of what the approaches to cancer treatment are, rather than get you to learn lots of pharmacology of anti-cancer drugs. So let's get into that. First of all, chemotherapy is all about trying to find weaknesses or points of attack on a bacteria, on a virus, or on a cancer cell that you can use to kill, to damage, to disrupt that cell or that organism without damaging the host, without damaging your own healthy tissues. And traditionally with cancer, the difficulty has been, of course, when a person develops a cancer, the cells that make up that tumour are their own cells. Admittedly, they're mutated cells, they're abnormal in some way, which is why they're forming a tumour, but they are still essentially the person's own cells. So they don't stand out as non-self. The immune system often has difficulty recognizing them, and similarly, finding targets on cancer cells is much more of a challenge than it is on bacteria or on viruses. So in the last couple of decades, there's been huge advances in cancer biology, the study of cancer cells. Because a tumour belongs to the person who has the tumour, it's not like a virus or a bacteria, which in a number of different people would be very similar. Everybody's cancer is fairly unique to themselves in many ways, because it started off as their own cells, which became mutated. So there's huge variations, not just between individuals with the same cancer, but also in the number of different cancers, the number of different tissues in which cancers can occur. So not only is it hard to find cancer targets, but it's also hard to find a cancer target that will give you a target to treat many different types of cancers. So there's been a lot of work done in cancer biology looking at the behavior of tumor cells. What do they do? What do they need in order to grow? How do they escape the normal control mechanisms? How do they escape notice by the immune system? What is it that they're doing? Where do they get all their resources from? How do they fuel their rapid growth? And all of those kinds of things. And the data that has come out of the huge amounts of research into cancer biology has produced targets that are allowing the development of much more specific cancer treatments now that don't give you the collateral damage that older treatments have produced. But have a look at what they all are in a second. So what do we know about cancer cells? This is a list, and it's not a complete list, but these are the major things that we know about cancer cells. That once a cell has picked up a certain number of genetic alterations that predispose it to uncontrolled growth, those are what we call oncogenes. In other words, it has a number of genes which are essentially telling it to grow in an uncontrolled way. Then cancer cells start to behave in these ways. We know that they produce their own growth factors. Now, growth factors are chemical signals which tell cells to divide and grow. So no mystery there as to what it is that's stimulating this overgrowth in a cancer. They also don't respond to the normal inhibitory growth signals, which normal cells do respond to. The signals which are put out, for example, when, let's say, you've got a bit of epithelium which has been damaged and it's healing, and the cells rapidly divide to fill in the hole, to repair the tear or whatever it is. But once the tear is repaired and the tissue has been closed up, the cells don't continue to divide. They receive inhibitory signals once they've contacted the cells that were there originally, which tell them to stop dividing. So they respond to those signals which say, okay, you've done enough division now, you can stop. Cancer cells don't do that. They just keep dividing. Even when in a restricted space and there's pressure and things which would normally stop cells dividing, cancer cells don't. Another thing that they are less responsive to is programmed cell death. That is, in our genetic material we carry genes which basically cause the cell to self-destruct. It's called programmed cell death if there is disruption to the cell's genetic material. The idea being that if a cell has picked up some serious mutations on its DNA, the last thing you want is for that cell to be able to divide and proliferate those mutations. So the best thing to do is, if the genetic code in a cell has been damaged in some way, that you would activate those suicide genes which cause that cell to destroy itself, so that it cannot pass on that damaged DNA. Cancer cells have abnormalities in the genes that initiate that programmed cell death when it needs to be triggered, and therefore they continue to survive and divide with serious genetic abnormalities. That's part of what it takes to be a cancer cell. They can keep dividing indefinitely. Again, they don't respond to the normal checks on the number of times that a cell can divide. They can sustain angiogenesis, meaning the development of new blood vessels, and this gives you a clue as to how they manage to bring in enough nutrients to supply a rapidly growing tumour. They send out growth factors which activate the growth of new blood vessels to that tumour, and they maintain that growth of blood vessels, so as the tumour grows, so does the blood supply, and nutrients are coming in at a high enough rate to sustain that high growth and metabolism. They metastasize. At some point, aggressive cancers start to spread. Malignant cells can be spread in blood, in the lymph, and set up secondary tumours in other tissues. It's the metastases of cancers which usually causes them to be fatal. Once they've metastasized, they're much more difficult to treat, and so what happens in order for cancer cells to transform into cells which go off to new sites is obviously an area of huge interest. Even if you couldn't stop a primary tumour, or you couldn't kill it completely, if you could stop it metastasizing, then you'd make a huge step forward. They also evade immune detection. Now, they're not really that obvious to the immune system anyway, but their metabolism allows them to almost cloak themselves from cells of the immune system. So when you put all of those hallmarks together, you can see what you're up against. You're up against something which is going to be very difficult to treat, but also you can see that all of those hallmarks as opportunities, because each one of them potentially could become a point at which you could try and attack the tumour cells, stop them growing, stop them surviving. If you could somehow block the production of growth factors or the effect of growth factors, if you could turn the ability to the self-destruct, if you can block that development of new blood vessels so that you can starve the tumours out, if you can somehow interrupt the process by which cells get to the point where they're metastasizing, if you can make them more obvious to the immune system, you can somehow label them, target specific immune cells to them, all of these potentially are points at which you could exploit those processes in order to treat cancers.